Today we're solving systems of equations by graphing. A system of equations is when two or more equations with the same variables are combined and solved together. In our case, we'll be using two equations in two variables. The solutions or answers we're looking for today are the point or points where the two lines meet. That's going to give us an x value and y value, or I should say x value and y value pairs that together satisfies both equations, which means they're going to make both equations true. Let's take a look at our first system. I have two very distinct equations, both with variables x and y, and that makes this a system. Since we're going to solve our systems today by graphing, we're going to take the time to graph each individual equation and find the point where they meet. Now, since this is all dependent on our graphing accurately, we need to be extremely careful with our graphing. They have to be 100% in the right place in order for this to work. So to make this as accurate as I can be, I'm going to take this first equation and change it into slope-intercept form because that's probably the most accurate way to graph. If I subtract 3x to the other side and divide everything by 2, I would get y equals -3/2 x plus 6. That tells me to start on the y-axis at 6, and using my slope of -3/2, from there I'm going to go down 3, right 2. And again, to make this extremely accurate, I would recommend repeating that slope over and over again until you can know exactly where that line is supposed to be. No estimating when you're solving a system by graphing. The second equation is already in slope-intercept form, so I'm going to start at -5 on the y-axis. And my slope of 4, or 4 over 1, tells me to go up 4, right 1. And again, I'm going to repeat that pattern and probably use a straight edge to make sure my line's in exactly the right place. In a system, we're looking for the point where the two lines meet. And these two lines meet at the point 2, 3. That point is our solution. When you're asked for the answer, you actually write the point, parentheses, comma, and everything, 2, 3. Now, of course, you want to save yourself a lot of headache, and we want a way to guarantee or double check that our answer is correct. Well, that's really easy if we simply take the x value and the y value and plug it into both equations and make sure that it's true. So I'm going to take a 2 and put it everywhere I have an x, and the 3 and put it everywhere I have a y. In the first equation, that's going to look like 2 times 3 plus 3 times 2 equals 12. Multiplying it out, I get 6 plus 6 equals 12, and since 6 plus 6 does actually equal 12, we know that this point satisfies the first equation. It's not enough to only check one equation in a system though, we need to check them both. So again, putting the 3 where I used to have a y and substituting the 2 in for x, I have 3 equals 4 times 2 minus 5, which when I multiply it out gives me 3 equals 8 minus 5. And since 8 minus 5 does equal 3, I can tell that this point satisfies both equations, and we're done with this system. Again, our actual answer is the point 2, 3. Let's look at another system. Again, we want our graphing to be as accurate as it can be, and the most accurate form to graph from is slope-intercept form. So I'm going to take this first equation and change it into slope-intercept form by subtracting 3x to the other side of my equation. That gives me y equals negative 3x plus 5. I'm going to do the same thing to the second equation. I get slope-intercept form, or isolate y, by dividing everything by negative 3. That's going to give me y equals negative 3x plus 1. Graphing the first equation, this equation tells us to start on the y-axis at positive 5, and our slope of negative 3, or negative 3 over 1, tells us to go down 3, right 1, repeating that pattern as much as I can to make sure my line is in exactly the right place. The second equation tells us to start at positive 1 on the y-axis and gives us the exact same slope, down 3, right 1. Drawing in my second line, I can see that these are parallel. Remember, the solution to a system is the point or points where the two lines meet. Do these lines ever meet? Not if they're parallel. Any equations or any lines where the slope is exactly the same will be parallel, so these lines never intersect. Hence, we have no solution. And on your paper, when you're asked for an answer, you write no solution. That's the second type of system that you'll probably see. Let's take a look at one more. Let's solve this system by graphing, and I threw this one in here because of that second equation. Graphing that type of line usually throws students for a loop. This is still a system because I have two very distinct equations and I still have matching variables. Graphing that first line tells me to start at negative 1 and go up 1, right 2 when using my slope. The second line, when I go to graph a line like this, don't let it throw you off. It's asking you to graph every point with a y value of 2. If I start plotting points where the y coordinate is 2, I would get points like 0, 2, 1, 2, 2, 2, negative 3, 2. And when I have some of those points on my graph, I can tell very much where my line is supposed to be. I could rewrite that equation if I wanted to. Y equals 0x plus 2. This is the type of equation with a slope of 0. These equations very much have a point where they meet. They meet at the point 6, 2, and that is our solution. I would take the time to plug that x value and y value into both equations and make sure that they satisfy both equations. But for now, in interest of time, we're going to move on to our next system. Graphing that first equation, starting at negative 3 with a slope of 2, gives me this line. Changing the second equation into slope-intercept form, I'm going to subtract the 12 to the other side, and then divide everything by 4. Y equals positive 2x minus 3. And where have we seen that equation before? Wasn't that our first equation? Well, if I graph this blue line starting at negative 3 and having a slope of 2, I get a line that fits right over the top of the line we had before. So think about it for just a second. The solution to a system is a point or points where the two lines intersect or meet. Since these two lines intersect at literally every point, how many points are there on a line? Isn't there an infinite number of points that make up a line? Well, if that's the case, in situations like this, we have infinitely many solutions There's no way that I can sit down and list all the points where they meet. So on my paper as my answer, I would actually write infinitely many solutions. Sometimes you'll just see infinite solutions, but it's more accurate to say infinitely many solutions. All right, let's kind of wrap this up and bring it together. First of all, to graph or to solve a system by graphing, make sure your equations are in slope-intercept form. I'm going to recommend that. That's not required, but I'm going to recommend that because that's the most accurate way to graph. Be extremely careful when you're graphing the lines. They must absolutely be perfect. So make sure to use a ruler and repeat your slope pattern over and over again. Look for the point where the two lines meet, or I should say point or points where the two lines meet. That is your solution. Remember, there are three different types of systems. Systems with only one solution, where your solution is a point. Slopes with no solution, or systems with no solution, when the lines are parallel and never intersect. And systems with infinitely many solutions, where your two lines are actually the same line. And finally, remember, if you do have only one solution, write your answer as a point. Just some vocabulary as a side note, words that you'll hear in the future. Systems can be consistent if they have at least one solution. An inconsistent system has no solution. An independent system has exactly one solution. That's different than at least one solution, right? And a dependent system has infinitely many solutions. Systems can fall into more than one category. If we have a system with infinitely many solutions, it can be dependent and consistent. If I have one solution, it can be independent and consistent. So, like I said, these are just words that you will hear in the future. You need to know what they refer to. All right, let's wrap it up for today. I hope you have a fantastic day, and I'll see you next time.